Hi everyone, it's me 𝗩𝗂 from 𝗏𝗏𝗄 Electronics. Today, I am going to show you how I design an activity tracker using an ESP32 and an accelerometer gyroscope module. This is a PCB board with all the assembled components. Here, we have the ESP32S3 module, the BNO085 motion sensor, and the 0.96-inch OLED display. By using the BNO085 accelerometer, gyroscope, and magnetometer with ESP32 processing, we will make a device called the IoT Activity Tracker. Using this device, we can monitor human activity and movement in real time. The tracker can measure steps, cadence, motion level, distance, calories, active time, and orientation. The OLED display shows important activity parameters such as step count, activity mode, cadence, motion level, distance, calories, active time, and roll-pitch-yaw orientation. In addition, the system features a Wi-Fi-enabled web interface, allowing users to monitor activity data in real time from a smartphone. The web dashboard displays live statistics, progress bars, donut charts, bar graphs, and trend graphs for better visualization. In this video, I will show you the basics of the BNO085 motion sensor and how it works with the ESP32. I will explain each section of the schematic used for designing this project. Then, I will show you how to make a custom PCB with a 3D view and finally assemble the hardware. Finally, we will write an Arduino code to make this IoT Activity Tracker project. So, without wasting any further time, let's get started. The PCB used in this project is sponsored by Avon, a global leader in PCB manufacturing and assembly. Avon produces high-quality PCBs with fast production and delivery times. For new users, there is currently a special campaign that includes free shipping and generous discounts, making PCB prototyping far more affordable. Welcome back again. Let us take a look at the BNO085 motion sensor first. The BNO085 is a 9-axis motion sensor that combines a 3-axis accelerometer, 3-axis gyroscope, and a 3-axis magnetometer in a single module. The accelerometer measures motion and acceleration, the gyroscope measures angular rotation, and the magnetometer helps detect direction and orientation. This sensor also includes an internal sensor fusion engine, which provides stable orientation data such as roll, pitch, and yaw. In this project, the BNO085 is used to track human movement. It provides step count, linear acceleration, gyroscope data, and orientation information to the ESP32. Based on this data, the ESP32 calculates activity parameters such as cadence, motion level, active time, distance, calories, and activity mode. Let us take a look at the schematic for this project. Starting from the power supply section, we are using a battery charging IC for charging and a single-cell lithium-ion battery. The battery is connected to this battery terminal and is charged through this Type-C USB port. The same port is also used for programming and USB serial communication. The device operates at a stable 3.3 voltage supply, so a voltage regulation section is used to power the ESP32 and sensors. For the ESP32 section, we are using an ESP32S3 module. A USB to TTL converter is used for programming and serial communication. The OLED display is connected through the I2C interface. The BNO085 sensor is also connected to the ESP32 through I2C lines using SDA and SCL with pull-up resistors. A push button is connected to GPIO 39 and is used for changing OLED pages and resetting the activity statistics. Now moving on to the PCB part. I converted the schematic to PCB and placed all the components as per the layout guidelines. The BNO085 sensor is placed carefully on the PCB to capture motion properly. The OLED display is positioned where the user can easily view the activity data. The routing is done based on signal requirements and component placement. Here is a 2D view of the board from the front side and also from the back side. Similarly, here is a 3D view of the board. The 3D view looks awesome, so the next step is to order the PCB. The Gerber files were generated and uploaded to Avon. Uploading the Gerber file is simple. You just select the board parameters like material, thickness, solder mask color, and quantity. And here you can see the total quote of just $1. And shipping is also free. If you want to order PCB at just $1, check the first link in the description. I placed the order, and within a few days, I received these high-quality PCBs. The finish, silkscreen, and through-hole placing were excellent. Next, I soldered all of the SMD components, which included resistors, capacitors, ICs, LEDs, USB port, ESP32 module, slide switch, JST battery connector, header pins, OLED display, and the BNO085 sensor section. The assembly was smooth, and the board looked professional after completion. Here is the ESP32S3 module. This is the 0.96-inch I2C OLED display. This is the Type-C USB port for uploading code and serial communication. This is the battery connector. The slide switch is used to turn the device on and off. The BNO085 sensor is placed here for motion and activity tracking. To test this device, I first connected a 3.7-volt lithium-ion battery and slid the switch to power on. If the code is already uploaded to the board, the device immediately starts operation and the OLED display shows the startup screen. You can also power the device through the USB Type-C port during programming or testing. Now, let's move to the programming part of this project. We are using multiple libraries here. For the BNO085 sensor, we are using the SparkFun BNO080 Arduino library. For the OLED display, we are using the Adafruit GFX and Adafruit SSD 1306 library. For Wi-Fi and web dashboard, the ESP32 Wi-Fi and web server libraries are used. You can change the Wi-Fi SSID and password in the code so that the ESP32 can connect to your Wi-Fi network and phone hotspot. The ESP32 reads motion data from the BNO085 sensor, including step count, linear acceleration, gyroscope values, and roll-pitch-yaw orientation. The program calculates important activity parameters such as cadence, motion level, active time, distance, calories, and peak motion. Based on cadence and motion intensity, the system classifies the activity mode as still using, walking, or running. The push button connected to GPIO 39 is used to control the OLED pages. A short press changes the page, and a long press resets the activity statistics. This makes the device easy to use without needing any external controls. From the web server section, the ESP32 sends live activity data in the JSON format. The web page is designed using HTML, CSS, and JavaScript. It displays the activity tracker data on a beautiful dashboard with cards, charts, progress bars, donut charts, and live trend graphs. To upload the code, you just connect a Type-C cable to the device. From the Arduino IDE Tools menu, choose the ESP32S3 development board and select the correct COM port. Then, click the Upload button and upload the code. Once the code is uploaded, the OLED display initializes and the BNO085 sensor starts sending data to the ESP32. During startup, the OLED shows activity tracker and the Wi-Fi connection status. If Wi-Fi is connected, the ESP32 IP address is displayed on the OLED for a few seconds. If Wi-Fi is not connected, the device skips the IP display and continues running locally with the OLED display. For your web monitoring, connect your phone to the same Wi-Fi network or phone hotspot used by the ESP32. Open the IP address shown on the OLED in a single mobile browser. This will open the web dashboard where you can view live activity data such as steps, cadence, distance, calories, active motion time, motion level, peak motion, roll, pitch, yaw, and sensor quality values. For testing the device in real-life conditions, go outdoors and keep the device in your pocket while walking. You can connect the ESP32 to your phone hotspot and open the IP address on your smartphone browser. Start walking slowly, then try normal walking and faster walking. You should observe the step count increasing, cadence changing, and the activity mode switching between still, walk, and run. The live web page also shows graphical data such as goal progress, active time percentage, statistical bars, cadence, trend, and motion trend. These visuals make it easier to understand the activity data in real time. Well, that's all from the video part today. All the detailed written guides related to this project can be found on the website article on How to Electronics. You can find the bill of materials, schematic, PCB Gerbil file, source code, and other instructions there. I hope you liked this video, so why not drop a like and hit the subscribe button? Finally, thank you so much for watching. See you in the next